To distinguish between an acid and base, we look at their properties. An acid tastes sour, like a lemon. Bases taste bitter, like baking soda. They are both corrosive, but acid corrode metals, while bases corrode organic material. When I react an acid and base together, it will always produce a salt and water, and we'll discuss what a salt is later. pH. On the pH scale, acids are less than 7, bases are greater than 7. However, on the pOH scale, acids are greater than 7, bases are less than 7. For both scales, when it's equal to 7, it is neutral. Using litmus paper, acids turn red, bases turn blue. When using phenolphthalein as an indicator, acids remain clear, bases turn pink. Bases are also slippery, like soap. Electrolytes, when dissolved, dissociates or break apart into ions. Since they are ions, the solution will conduct electricity. The more ions are more concentrated, the more conductive the solution is. Examples of electrolytes are acid, base, and salts. There are 3 ways we could identify acids and base. The first one is Arrhenius. Arrhenius acids give off H plus ion, so hydrogen ions, while bases give off OH minus ions. So when HCl breaks apart or dissociates, it has a hydrogen ion. Therefore, it is Arrhenius acid. When I take NaOH and dissociate it, it produces an OH minus ion. So this is an Arrhenius base. However, Arrhenius acid-base definition is very limited, especially for bases, because all bases do not contain a OH minus ion. The better definition of an acid-base is a Bronsted-Lowry acid and base. An acid always donates an H+, while a base always accepts an H+. So in the example below, HA is a Bronsted-Lowry acid. It has the ability to donate a hydrogen to the B, which is a Bronsted-Lowry base. Since it is the base, it will accept the hydrogen and become Hb+. We have to account for signs when we do Bronsted-Lowry acid. Every single time it gains a H+, the charge goes up by a +1. Every single time it loses an H+, the charge goes down by a -1. Since the Bronsted-Lowry acid donated the H+ to the base now becomes Hb+. It went from a neutral atom to a charged ion. This is the conjugate acid of the Bronsted-Lowry base. Conjugate pairs always differ by 1 hydrogen plus. Since the Bronsted-Lowry acid gave away an H, it becomes A-, which is the conjugate base of the Bronsted-Lowry acid. So HA and A- become a conjugate pair. They differ by 1 hydrogen. Since HA lost an H+, now the charge is A-. Pause the video, try these problems on your own, and then check your answer. In number 1, HCO3- is the Bronsted-Lowry acid, and NH3 is the Bronsted-Lowry base. The reason I know HCO3- is the Bronsted-Lowry acid is if I check the opposite side, HCO3- became HO32-, so it lost a hydrogen ion or it donated a hydrogen ion. So that means that HCO32- is my conjugate base. These are a conjugate pair, and NH3 accepted a hydrogen, so it is a Bronsted-Lowry base, and its pair is NH4+, which is my conjugate acid. Remember, conjugate pairs differ by 1 hydrogen. My HCl is my bronzyloric acid. Here, my water is going to behave like the bronzyloric base. HCl is going to donate a hydrogen to water and become H3O+. So this becomes my conjugate acid. So these are a pair. And my HCl became Cl-, so that's my conjugate base. So these are a conjugate pair. In number 3, HOCl is my bronzyloric acid. Again, if you can't tell, look at the product side. HOCl became ClO-, so it donated H+. So this is my conjugate base. So these are my conjugate pairs. NH3 is my bronzyloric base, and it accepted a hydrogen. It became NH4+. So that's my conjugate acid. Acetic acid, you should know it's an acid, so that's my bronzyloric acids. Here my water is my bronzyloric base. Acetic acid here gave away a hydrogen to water and it became acetate ion. So this is my conjugate base. And my water took an hydrogen, so it became hydronium ion or H3O+, and that's my conjugate acid. My sulfuric acid is a bronzyloric acid. My hydroxide ion is my bronzyloric base. The sulfuric acid donated a hydrogen to the OH-, and so it became HSO4-, so this is my conjugate base. And H2O became my conjugate acids. So my pairs here are H2SO4 and HSO4-, OH-, and water. My sulfuric acid is still bronzyloric acid. My water here is my bronzyloric base. The acid is going to donate a hydrogen to my water. H2SO4 becomes HSO4-. This is my conjugate base. This is a pair right here, conjugate pair. And my water becomes hydronium ion, so this is my conjugate acid. So these are a pair. In my last problem, CO3 2- is my bronzyloric base. My water is my bronzyloric acid. The water must donate a H to my CO3 2-, it becomes HCO3-, so this is my conjugate acid. So these two are a pair, and then water is paired with OH-, which is my conjugate base. So first thing you want to do is identify your bronzyloric acid base. The acid will donate a H+, the base will accept an H+. If you are not sure of which is the acid or base, check the product. If the product is missing a hydrogen, that means that is my conjugate base. So the one that gave off the hydrogen on the opposite side, or the one that actually contains the hydrogen on the opposite side, is your bronzyloric acid. And remember, conjugate pairs differ by one hydrogen. The final way we could define an acid is a Lewis acid base. Acids are electron acceptors, base are electron donors. So we have A+, which is a Lewis acid, plus B-, which is a Lewis base, and they combine together to produce a coordinate covalent bond. So if we have BF3 and we draw the Lewis dot structure for BF3, B is the central atom, and we have fluorine surrounding it, 6 electrons. Boron is one of the exceptions, and it could have less than the octet rule. If I draw the Lewis dot structure for NH3, we have N, we have hydrogen, fulfills the duet, and we have a lone pair. So BF3 is deficient 2 electrons, looks for molecules that have lone pairs or have electrons to donate. So BF3 is a Lewis acid because it's looking for electrons. NH3 is a Lewis base because it has the ability to donate electrons. So if I draw my Lewis dot structure of the two together, this is what it looks like, and this is called a coordinate covalent bond. And now both of them fulfill the octet rule. So here, if we draw the Lewis dot structure for Cn-, it looks like this. For HCOCH3, it looks like this. Cn minus is my Lewis base because it has the electrons to donate. HCOCH3 is my Lewis acid, and they will combine like this to form a coordinate covalent bond. Amphoteric substances can behave as an acid and base. Example of an amphoteric substance is water. When we were doing Bronze lauric acid base, depending on what it was reacting with, sometimes water behaved like an acid and sometimes water behaved like a base. So if I have these examples here, we have two waters. This is going to auto-ionize. So here we will have a Bronze lauric acid as water and Bronze lauric base as water. The water, that is the acid, will donate a hydrogen and become OH minus. So this is my conjugate base. So these are a pair. And the water, that is the Bronze lauric base, will accept the hydrogen and become H3O plus. So this is my conjugate acid. And these are a conjugate pair. In the next example, HCN is an acid. So this is my Bronze lauric acid. So water behaves like a Bronze lauric base. HCN must donate the hydrogen to the water. So HCN becomes Cn minus. So this is my conjugate base. These are a pair. And the water and the hydronium will be a pair, conjugate pair. In the last example, water will behave like a Bronze lauric acid because NH3 is a weak base. So it's a Bronze lauric base. The water will donate a H to the ammonia and become OH minus. So water and OH minus are a conjugate pair, and this is my conjugate base. And NH3 will accept the hydrogen and become NH4 plus, and they will be a conjugate pair, and this will be my conjugate acid. So depending on what the substance is combined with, they will behave like an acid or a base. To understand how acids and bases work in solution, we need to memorize the strong acids and strong bases. The strong acids are HCl, HBr, HI, HNO3, HClO4, H2SO4. Anything that is not part of the 6 given will be considered to be a weak acid. Strong bases are everything in group 1 except for hydrogen, because HOH makes water. So lithium hydroxide, sodium hydroxide, potassium hydroxide, rubidium hydroxide, cesium hydroxide, and francium hydroxide. In group 2 is calcium and below. Calcium hydroxide, strontium hydroxide, barium hydroxide. These 4 here are strong bases. However, a lot of times they won't use it in problems because they're mostly radioactive. The reason you need to memorize strong acid and strong bases, because if it is not listed here, it will be considered weak. The relative acid and base strength is dependent on how strong the acid and base are. When it is a strong acid and base, it dissociates 100%. Acid and base does not exist. It only exists in ion form. Therefore, their conjugate, whether it's acid or base, are weak. If it's a weak acid or base, it only partially dissociates. Therefore, their conjugate are considered to be strong. The reason this is important is the equilibrium favors the reaction towards the weaker side. The reason the relative strength of acid and base are important is because equilibrium favors reaction, moves from H plus from acid to base to form the weaker acid or weaker base. In other words, the equilibrium lies towards the weaker acid and weaker base because they are more stable species and they have lower energy. Not only does it tell you where the equilibrium lies, but it will also tell you how to write their equations to calculate the equilibrium concentration of all the species correctly.